Hello. In the last chapter or maybe the last discussion, we have discussed about the mechanical properties of the metals. In this particular lecture, we are going to discuss about the other properties of the metals. So, here actually already we have discussed about the mechanical properties. So, in this particular lecture, we are going to discuss about the electrical property, thermal property and the magnetic property of that metals, then chemical property like reactivity, toxicity and the corrosions. So, first we will discuss about the electrical properties of the metal itself. So, in the when we are talking about the electrical properties of the metals, so first whatever the laws generally we are follow, that is known as the Ohm's law. So, what the Ohm's law states? Ohm's law directly states that V is directly proportional to the I. What is V? V is known as the voltage and I is known as the current passing through. So, if we derive that formula properly, then we will get that V is equal to IR. Here R is the resistance of that particular material. So, generally the units of V, I and R are volts, amperes and the ohms. Now, when the electricity is passing through any materials, so sometimes it resists also that passing of that electrons. So, that is known as the electrical resistivity. So, electrical resistivity is depend on the resistance R, specimen cross sectional area. So, the cross sectional area of that particular wire, the total distance travelled. So, the distance between the 2 points at which the voltage is measured. So, the units of rho is ohm meter. So, generally the rho is equal to VA by IL. So, electrical conductivity, it is just the opposite of that electrical resistivity. So, sigma is equal to 1 by rho, which is nothing but the IL by VA. Next, we will discuss about the energy band structures of that particular materials. So, from the quantum mechanics describes about the electron in a solid. In a solid, many atoms are brought together, so that the split energy levels from a set of bands separated by the forbidden energy gap. There are two types of bands called the valence band and another one is known as the conduction band. Bound outer shell electrons are valence electrons. Valence electrons are occupied in the valence band itself. So, in this particular case you can find that these all are the valence band for insulator materials, semiconductor materials and the metals. So, bond break from energy, like if we give certain energy to that, so the bond may break. What kind of energy it is? Maybe thermal energy, electrical energy or maybe the vibrational energy in the lattice, which promote the electron to the conduction band. That means, electron will jump from the valence band to conduction band. Conduction is the motion of free electrons. So, when the electron will move, then automatically the current flow will start. So, in case of metals, Fermi level lies inside the conduction band and this band is partially filled with electrons, overlapping of conduction and the valence bond. Valence electrons can freely transit to higher energy state in the conduction band. Of course, the jumping will be taking place, therefore, applied voltage will cause their drift electrical current. Metals are highly conducting in nature. So, in this particular case you can see that the how the electron density is changing and also the electron is jumping from the valence band to the conduction band. So, when the electron is jumping from valence band to the conduction band, so a hole is created in the valence band itself. Next, we will discuss about the electron mobility. From the name itself you can understand that it is the freeness or maybe the movement of the electron. So, in solid state physics, the electron mobility characterizes how quickly an electron can move through a metal or semiconductor when pulled by an electrical field. So, when electrical field E is equal to 0, electron moves randomly throughout the crystal in the conductors. Net current is totally 0. No drift velocity you can find over there. So, in this particular case you can find that net electron motion for the scattering events. So, it is opposite the electron field, and then when an electron field is applied, so in that case electrons are accelerated in a single direction opposite to that electron field by virtue of their negative charge and thus flow of charge in electrical current. Of course, because there will be plus and minus, so automatically if there will be plus, then automatically the electron will be attracted to other, the current will flow in the opposite directions. This acceleration of electrons is opposed by the internal damping force or frictional force due to scattering of electrons by imperfections in the crystal lattice. Nothing, in a simple word, we have to agitate that electrons to flow from one side to another. What is the scattering phenomenon? It is manifested as a resistance or to the passage of an electric current. There are mainly two parameters used to describe the extent of this scattering. One is called the drift velocity, another one is called the mobility of an electron, which is known as the electron mobility. When scattering or collisions occurs in between the electron loses the kinetic energy. Of course, they will hit each other, so they will lose the kinetic energy, which will transfer to the lattice of that metal, and then electron lattice scattering will be taking place, which will help to existence of the resistance and warming up of a metal like electrical heaters. Simple, for when we are using the electrical heaters, that means actually in between that the electron are colliding each other, due to that their kinetic energy is transformed into the heat energy. Or second option is that change the direction of the motions of the electron. So, by these two phenomenon we can do the scattering phenomenon or maybe the scattering of the electron. Next is called the drift velocity. So, the drift velocity, generally Vd, represents the average electron velocity in the direction of the force imposed by the applied field. It is directly proportional to the electric field as follows, like Vd is directly proportional to E. So, E is the applied field. That means Vd is equal to mu E E. Mu E is nothing but known as the electron mobility, which is an indication of the frequency of scattering events. Its units are square meters per volt second. The conductivity of most materials may be expressed at sigma is equal to n E mu E, where n is the number of the free or maybe the conducting electrons per unit volume, and E is the absolute magnitude of the electrical charge of an electron, that is 1.6 into 10 to the power minus 19. So, N metal is more higher than the N semiconductor, more higher than the N insulator. So, that means the sigma of that metal is more higher than the sigma of the semiconductor, then more higher than the sigma of the insulator. So, sigma metal is more greater than the sigma insulator and the sigma semiconductor. So, the conductivity, from this particular case we can get the information about the conductivity. So, conductivity of the metal is more higher than the semiconductor, semiconductor conductivity is more higher than the insulator. And in the right side bottom image you can get that when there is a charge of minus and plus. So, when the plus sign is there, so automatically the all the electrons is going towards in these directions. When the polarity will change, then always the electron movement will be in the opposite side. So, automatically the kinetic energy will be formed inside the material itself. Next we will call about the electrical resistivity. It is nothing, it is the opposite of that electrical conductivity. So, electrical resistivity is the reciprocal of the electrical conductivity, which is denoted by rho, which is nothing but the rho is equal to 1 by sigma. So, since crystalline defects serve as scattering centers for conduction electrons in metals, increase the resistivity, that means it lowers the conductivity. The concentration of these imperfections depends on temperature, compositions of that particular material and the degree of cold work of a metal specimen. Total resistivity rho of a metal is the sum of the resistivity contributions from thermal vibrations, impurities and the plastic deformations. That is the scattering mechanism, which is known as the Matheson's rule, act independently of one another. So, Matheson's rule is represented by this mathematical formula, rho is equal to rho T, that means due to the thermal vibrations, then rho I, that is due to the impurities and the plastic deformations, that is rho D. So, any one of that if it will increase, so automatically the rho value or maybe the electrical resistivity of that particular material is going to be increased. Now we will discuss about the factors which affect the electrical resistivity of the metal itself. So first is called the influence of the temperature. So for the pure metal and all metal alloys, the resistivity rises linearly with temperature. So if we increase the temperature of that particular material, so its electrical resistivity will automatically increase. In these particular equations, you can find that rho T is equal to rho 0 plus A T, where rho 0 and A are the constants for each particular metal. So from that we can conclude that if we increase the temperature, so thermal vibrations and lattice defects will also increase, which in turns increase the electron scattering, and then due to that the thermal resistivity component will also increase, then the final result will be automatically the electrical conductivity is going to be decreased. Next is called the influence of plastic deformations. So plastic deformation also raises the electrical resistivity as a result to increased the number of electron scattering dislocation. So dislocation is taking place inside the materials. From the right hand side figure, we can see that electrical resistivity versus temperature of that curve of a copper and 3 copper nickel alloys, one of which has been deformed. Thermal impurity and deformation contribution to the resistivity are indicated at 100 degree centigrade. So automatically from this particular case, you can see that when we are going to change the constituents of that materials, that means we are going to add the more impurity to the virgin materials or maybe different materials additions, so their resistivity is going to be changed. Next is called the influence of impurities. So for addition of a single impurity that forms a solid solution, impurity resistivity is related to the impurity concentrations in terms of atom fractions at 100%. So that is denoted by the rho I, which is nothing but the rho I is equal to ACI in bracket 1 minus Ci, where A is a composition independent constant, impurity and host metals. For 2 phase alloy, generally consisting of alpha and beta phases, generally we can see it for the stainless steel or maybe some other kind of materials. So rho I is equal to rho alpha V alpha and rho beta and V beta, where alpha and beta are the 2 different phases. So Vs and rho s represent the volume fractions and individual resistivities for the respective phases. So for example, the influence of nickel impurity, in the right hand side you can see that we are going to increase the nickel percentage from 0 to 50, and how the electrical resistivity is going to be changed. So influence of nickel impurity additions on the room temperature resistivity of copper is demonstrated up to 58%. So actually this material is made of copper, where we are going to increase the nickel percentage inside that particular matrix. So over this composition range, nickel is completely soluble in copper. Nickel atoms in copper act as scattering centers, and increasing the concentration of nickel in copper results in an enhancement of the resistivity. So how the resistivity is going to be increased in this particular case. Next we will discuss about the thermal properties of that metals. So if we discuss about the thermal properties, so first the heat capacity comes to our mind. So what is heat capacity? The amount of energy needed to raise the temperature of a substance absorb heat from the external surroundings. It represents the amount of energy required to produce a unit temperature rise. Simple, from outside we are giving the temperature by which a degree of temperature is going to be increased inside the metal. In mathematical terms, the heat capacity is C. Generally it is denoted by capital C. So capital C is equal to dq by dt, where dq is the energy required to produce a dt temperature change. Unit of heat capacity is joule per Kelvin or maybe the joule per degree centigrade. 2 ways to measure these properties, because there are 2 ways by which we can measure the heat capacity of any metals. So first one is known as the heat capacity at constant volume and heat capacity at constant external pressure. So generally the heat capacity which is at constant external pressure, which is nothing but known as the Cp, is always greater than the Cv, that means heat capacity of a constant volume at room temperature or below than that. Now we are going to discuss about the thermal expansion. So thermal expansion is a material property in which a material expands upon heating and contract when cooled and has units of reciprocal temperature, that is 1 by degree centigrade. The change in length with temperature for a solid material may be expressed as follows: Lf minus L0 by L0. Lf is the final length with the temperature change from T0 to Tf, and L0 is the initial temperature, is equal to alpha L Tf minus T0. So, here the parameter alpha L is called the linear coefficient of thermal expansion. If a material expands as its temperature rise, this means the same mass of material occupy a large volume, but its density will decrease. Volume change with temperature is del V by V0 is equal to alpha V into del T. So, where del V and V0 are change in volume and original volume with the temperature change del T. The parameter alpha V is called the volume coefficient of thermal expansion. So, here from this we can understand that alpha is called the linear coefficient of thermal expansion and alpha V is known as the volume coefficient of the thermal expansion. Now, example of the thermal expansion means what is the mechanisms behind it. So, most analog thermometers are made using mercury, which is the only metal in a liquid state at room temperature. Coefficient of thermal expansion of mercury is 181 into 10 to the power minus 6 per Kelvin. When heat energy is transferred to the bulb filled with mercury, the liquid expands and move up to the tube due to change in volume brought about by change in temperature. So, in this case we are going to increase the heat. Generally for measuring the fever we are using this kind of thermometer, where with our body temperature increases, so automatically the volume expansion of that mercury is taking place, by which we can measure the body temperature at that particular time. So, actually what mechanisms? Actually when the material is into the room temperature or maybe into the cold conditions, all the particles in the solid vibrates, but at higher temperature they vibrate faster and take up more space to expand, but particle size are remain same. So, particle size is not going to be changed, only the vibrations of that particular particle is going to be increased. Now, we are going to give another best example is called the bimetallic strips. So, a bimetallic strips, as we know that is a combinations of the brass and iron. So, a bimetallic strip is used to control the thermostats and also used in fire alarm, hair dryer or hot glue gun. So, what is happening actually? So, when it is getting the temperature, the thermal expansion of these two different metals like brass and iron are totally different. So, in this particular case the brass thermal expansion is more higher than the iron. So, that is why it is bending. So, it is made of two metal strips stuck together. One metal expands more than the other when they are heated. These cause the strip to bend. Next we will discuss about the thermal conductivity. So, it is the property of a material to conduct the heat which is transported from high to low temperature region of a substance. Mathematically it is denoted by small q, which is nothing but is equal to minus k dt by dx, where q is the heat flux per unit area, that is watt per meter square, and k is the thermal conductivity, watt per meter per Kelvin, and dt by dx is the temperature gradient through the conducting medium. So, this is the examples of different materials, says like aluminum at 25 degree centigrade, its specific heat is 0.215, coefficient of linear expansion is 25, thermal conductivity means k value is 2.37. When you are talking about the copper, its specific heat is 0.092, coefficient of linear expansion is 16.6 and the thermal conductivity is 3.98. When you are talking about the platinum, its specific heat is 0.032, coefficient of linear expansion is 9, thermal conductivity is 0.73. So, in this particular case what we are getting, that in the cold temperature that material behaves is differently. When we are heating that materials, the electric field actually it is going into the opposite directions. So, when the material is heated up more, so automatically the electrical resistivity of that material is going to be increased. Mechanisms of the heat conductions. So, heat is transported in materials by both lattice vibration waves, which is known as the phonons, and free electrons. So, the total conductivity k is lattice vibrational conductivity Kl and the electron thermal conductivity which is known as the Ke. Metals are good conductors of heat because relatively large number of free electrons exist that participate in thermal conduction. Since free electrons are responsible for both electrical and thermal conduction in pure metals, theoretically suggested that two conductivities should be related according to Weidmann-Franch law, which is known as the capital L is equal to small k by sigma T, where sigma is the electrical conductivity, T is the absolute temperature and L is a constant. The theoretical value of L is 2.44 into 10 to the power minus 8 ohm per watt per Kelvin square, should be independent of temperature, and the same for all metals if the heat energy is transported entirely by the free electron itself. Then we will discuss about the magnetic properties. So, magnetic properties, generally basic parameters used to study of the magnetic behavior of materials is known as the, first is known as the magnetic moment. So, magnetic moment is magnetic dipoles are equivalent to electric dipoles, consist of north pole and south pole, and distance in between these two poles is known as, suppose it is 2L. So, what will be the magnetic moment? The m into 2L. So, where m is the strength, and if we discuss about the magnetic field strength, it is generated by means of a cylindrical coil or maybe the solenoid consisting of n closely spaced turns having a length L and carrying a current of magnitude I. So, H is equal to N I by L. A circular current loops is equivalent to a magnetic dipole, mu m is equal to I into A. So, in this particular case we are having that cylindrical coil, and then we are giving a current from this side and the current is coming through this side, and the magnetic field will be generated inside this solenoid coil. Then there are some other properties also. Magnetic susceptibility, which is known as the chi, is equal to magnetizations divided by the magnetic field strength is equal to m by h. It does not have any unit because both are having the same unit. Next we will discuss about the magnetic flux density B within a solid materials. So, magnetic flux density is directly proportional to the H, that means field. So, here B is equal to mu H, which unit is Weber per meter square. Here the mu is the magnetic permeability, which is property of a specific medium through which H field passes. Unit of mu is Weber per ampere meter. In a vacuum, B0 is equal to mu 0 H, where mu 0 is the permeability of a vacuum, a universal constant which is a value of 4 pi into 10 to the power minus 7 Weber per ampere meter. Next we will discuss about the relative permeability, which is known as the mu r is equal to mu by mu 0. It is also does not have any unit. Then relations between Hb and m is B is equal to mu 0 into m plus H, and relative permeability mu r and susceptibility chi is B is equal to mu 0 H is equal to mu 0 into mu r H, or mu r is equal to 1 plus chi, which we can get from this particular image. So, here you can find that I current is working over there, N is the number of turns, here H is known as the field passes through this, and L is the total length of that particular solenoid. So, in this particular case by we know H, we know B, by which we can calculate the magnetic susceptibility, magnetic flux density, relative permeability, relative relations between Hb and m, and the relative permeability and the relative susceptibility. So, from that we can do a very good comparison in between the magnetic materials. So, generally the magnetic materials is divided into three parts. One is called the diamagnetism, paramagnetism and the ferromagnetism. Diamagnetic substance are those substances which are freely repelled by a magnet. So, if we take that material towards the magnet, so it will be repelled by that magnet itself. Paramagnetic, it will partially allow that material to come closer. Ferromagnetic, it will fully allow that material to come closer to the magnetic field. Second point, when placed in magnetic field, the lines of force tend to avoid the substance for the diamagnetism. it will partially allow that materials. The lines of force prefer to pass through the substance rather than air. Ferromagnetism, the lines of force tend to crowd into the specimen, means it will fully allow that lines. For diamagnetism, when a diamagnetic substance is placed in a magnetic, it is weakly magnetized in the direction opposite to the including field. When a paramagnetic substance is placed in a magnetic, it is weakly magnetized in the direction of the including field. When a ferromagnetic substance is placed in a magnetic field, it is strongly magnetized in the direction of the including field. So, permeability mu value for the diamagnet is less than 1, paramagnetism is greater than 1, and for the ferromagnetism also it is greater than 1. Susceptibility chi value for the diamagnetism, it is less than 0, it does not depend on temperature. Susceptibility is positive for the paramagnetism, small and temperature dependent, and for ferromagnetism it is positive, large and totally temperature dependent. Example of the diamagnetism materials are copper, silver, mercury, gold, zinc, antimony and bismuth. For paramagnetism it is aluminum, chromium, sodium, titanium, zirconium, and ferromagnetism it is iron, cobalt, nickel, etc. So, what is the origin of that magnetic moment? So, there are 3 sources of magnetic moment in an atom of any material. First one is called the orbital motions of the electron, second is called the spin motion of the electron, and third one is called the nuclear spin. So, if the vector sum of all the contributions is 0, then net magnetism is 0, material is non-magnetic material. Metals have different magnetic phases depending on the temperature of the environment in which they are located. As a result, a metal may exhibit more than one form of magnetism at a time. Iron, for example, loses its magnetism, becoming paramagnetic when heated above 1418 degree Fahrenheit or maybe 770 degree centigrade. The temperature at which a metal loses magnetic force is called the Curie temperature. Iron, cobalt and nickel are the only elements that in metal form have Curie temperatures above room temperature. As such, all magnetic material must contain one of these elements like iron or maybe cobalt or maybe the nickel. So, here just this image is simply giving us the informations about the orbital motions, the spin motions of the electrons and the nuclear spin. Next we will discuss about the chemical properties of metals. So, reaction of metals with the oxygen, this is the normal phenomena generally we can find while using some metals. So, almost all metals react with oxygen to form the metal oxides, but different metals react with oxygen at different intensities. For example, sodium metal is always kept immersed in kerosene oil, because if we keep it open, it reacts to vigorously with oxygen present in air and it will catch the fire. So, that is why we are putting or maybe while keeping that sodium in the lab, generally we are dipping it into some kerosenes. On heating, magnesium metal burns in air, giving the magnesium oxide MgO. Sulfur reacts with oxygen of air to form the acidic sulfur dioxide. So, generally metal oxides are insoluble in water, but some metal oxides are able to dissolve in water to form metal hydroxides or alkali. For example, the sodium hydroxide which is known as the NaOH. Then reaction of the metals with water. Metals which are very reactive can react even with cold water, while the other metals react with hot water or with steam. So, it actually depends upon the chemical properties of that particular metals. Sodium and calcium metal can react with cold water and it can form the calcium hydroxide and sodium hydroxide. Magnesium and zinc react with the hot water, which can form the magnesium oxide and the zinc oxide, and they will evolve the hydrogen gases from that particular reaction. When a metal reacts with a dilute acid, then a metal salt and hydrogen gas are formed. For example, 2Na plus 2HCl, it can form the sodium chloride and the hydrogen gas. Magnesium and hydrochloric acid form the magnesium chloride plus hydrogen gas. Zinc and hydrochloric acid forms the zinc chloride and the hydrogen gas. So, the metal can react with the water, metal can react with the acid, metal can react with the air. Next we will discuss about the toxicity of the metals. Yes, of course, we are using nowadays, we are using that metals for the biomedical applications also, but there are some metals like magnesium which the toxicity is very less, but there are some other metals which is very highly toxic in nature. So, mercury is highly toxic in vapor form, but lead, cadmium, arsenic are more toxic in their cationic form. Toxicity arises from strong affinity of the heavy metals cations for sulfur. Certain toxic elements that are beneficial for certain organisms or under certain conditions. Example includes vanadium, tungsten, cadmium. So, these are some sorts of helpful toxic materials. Corrosion of metals and their alloys. Corrosion environments, this includes the following: atmosphere, marine atmosphere, aqueous solution, acids, bases, inorganic solvents, molten salts, metallic compounds in solutions and the human body. Corrosion is the process of dissolutions of metals when exposed to corrosive environment. Of course, you have to take out that material into the corrosive environment. It can be explained by the electrochemical reactions that plus ion and the electron will be generated. For corrosion reactions to proceed, the number of electrons released in the anionic reaction must be consumed by some cathodic reaction which takes place at some location on the surface of metal. Examples: rusting of iron. Iron metal reacts with the oxygen to produce the iron oxide or maybe the rusting. So, here you can find out the iron, and when it is coming into the contact with the oxygen, it is form the Fe2O3 which is here. So, redox reaction is taking place. So, the actually the iron and the oxygen, the interatomic bonding is taking place over there. So, due to that the rusting formation is taking place. Corrosion rate or corrosion penetration rate, it is defined as the thickness loss of the material or rate of material removal per unit time. So, generally it is denoted by the CPR, corrosion penetration rate, is equal to Kw by rho AT, where W is the weight loss after exposure time, rho is the density, A is exposed surface area, T is the exposed time and capital K is the constant. Where CPR in mils per year, generally the K value at that time is 534, W in mg, rho in gram per centimeter cube, area in centimeter square and the time is in hour. Where CPR in millimeter per year, then K is equal to 87.6, W in mg, rho in gram per centimeter cube, A in inch per inch square and T is in hour. Now, we will discuss about that use of all these metals. So, metals, as I told at the starting of this particular lecture, that we are using it for the various applications, numerous applications such as structural, for making the building, architecture, concrete reinforcement, etc., automotive, parts of machines, chassis, drivetrain, body parts, etc. For aerospace, generally aircraft applications, we are using the aluminum alloy. Marine, for ship hull structure, engines, etc., we are making. Defense, for tanks and weapons we are using. Consumer products, food containers, toys, utensils and tool, etc. Industrial, electrical wires, chemical plants and thermometers. But in a simple term, if I can say that this is a very small applications, there are n number or maybe plenty of applications where we are using these metals. So, generally from the right hand side image you can find that whatever I have already discussed, we are using for several purposes in the chemical plant, aircraft parts, cooking utensils, galvanizing, machinery, car bodies, electrical wiring, making brushes or maybe any kind of alloys and everything. So, now we are going to summarize these materials. So, from these particular lessons we have learnt about the metals and their various properties. Metals are very important for everyday life and metals are having a very wide range of applications or maybe the properties like thermal properties, electrical properties, magnetic properties and some chemical properties. Due to that we are going to use these metals for very large applications. Thank you.